All right, here are our solutions to centripetal acceleration and force. So I'm going to go a little bit deeper into this. What's needed to make an object move in a circular path? So what we need is a force that constantly pushes our object, that constantly points towards the center of the circular path that we're interested in. All right, so that's a pushing the object towards the center or pulling the object towards the center. Or if you want to think about it a different way, we need some sort of constraining force to make the object go in a circle. Think about a ball on the end of a string. The string is the force that's constantly pulling it towards the center. The string is the constraining force that we have. Okay, for each of these situations, determine what force is causing the thing to move in a circular path. The answer to that question is never, it's the centripetal force. The answer to that question is a specific kind of force that we've dealt with. So a boy sitting on a revolving merry-go-round, guess what? Friction. Friction is keeping him from sliding off. Friction is keeping him from moving in a circle. So friction keeps him from sliding. So friction is the thing that's keeping him going in a circle. A swinging tetherball on a rope. Well, here we have the rope. So it's the force of tension that's keeping the ball in a circle, that's constraining it, that's applying the force towards the middle the whole time. A satellite in orbit around the Earth, well, it's gravity that's pulling it back towards the Earth the entire time. And then a car going around an unbanked level curve, well, that's friction. Think how well that does when there is no friction. The car just goes off on a straight line. So the car going around an unbanked curve has friction acting on it. All right, there's a fair ride called the gravitron. If you stand against the wall, it begins to spin. As the ride gets faster and faster and faster, the floor drops away, but the rider stays stuck to the wall. So we want to explain what's going on there. So what's going on there is we have friction keeping them from sliding down. Now friction depends on sliding down the wall. Friction depends on the normal force. The thing that keeps them moving in the circle is the normal force from the wall. That's what keeps them going in a circle. Normal force from the wall. The more normal force we have, the more friction we have. And that normal force from the wall points to, that normal force from the wall points to the center of our circle. That's another reason we know it's going to be the force that's causing us to go in a circle. It's the one that's pointing towards the center. All right, so number 4, we have a ball that's tied to a swing and swung in a clockwise horizontal circle as we see in that diagram to the right. What direction does the ball accelerate? It's towards the center, always. Our centripetal acceleration is always towards the center. And it's going to be the same size with an always changing direction. All right, so the acceleration always points to the center. You notice as we go around that circle, it's either up, left, right, or down. It's changing direction even though it's pointing at the same spot. What force causes the ball to accelerate? Well, this ball is tied to a string, so the force that we have is tension. Tension is the force that pushes or pulls to the center. That's the thing that's causing us to accelerate. Again, that force acts to the center. The force that makes us go around in a circle has to point to the center. There are no forces pointing outwards. And then if we want to see the velocity, that's going to be tangent to our circle the entire time. So the velocity points as shown. And then the net force points in. So that's a picture of the velocity and the forces there. If the string were to be cut at the top of the circle, looking at that, the ball would move in the direction of its velocity. And at the top of the circle, that's to the right. All right, next question. We have a ball of mass 5 kilograms swung in a horizontal circle at a rate of 2 revolutions per second. We want the linear speed of the ball. So what I like to do first, I see that the frequency is 2 revolutions per second. The period is 1 over the frequency, so the period is 0.5 seconds. If I want the velocity, or the linear speed of the ball, it's going to be 2 pi r, the circumference of the circle, divided by how long it takes to go around the circle once. So, looking at that, it's 2 times 3.14 times the radius of 0.75 meters divided by the time it takes to go around once of 0.5 seconds. So we get 9.42 meters per second as the velocity that the ball has. Find the centripetal acceleration of the ball. Well, to get the centripetal acceleration, that's going to be v squared over r. Every time we get centripetal acceleration, this is what we're going to use. So the centripetal acceleration is going to be 9.42 squared divided by 0.75. Put that in your calculator, and it comes out to be 118.3 meters per second squared. Find the force of tension on the string. Well, my net force is equal to tension. That's one way of getting the net force, just looking at the forces acting on our object. The other way to get our net force is to do mass times acceleration. Well, guess what? We're moving in a circle, so that's going to be centripetal acceleration, and we just found that. So we could use that to get our net force as 5 kilograms times 118.3 meters per second squared. It gives me a net force of 591.6 newtons. And from the other net force equation, I know that has to be equal to the tension. All right, for question 5, we're on a roller coaster, and the radius of the loop on the roller coaster, like you're doing a loop-to-loop, or on the Titan, maybe one of those big horizontal loops that you do, has a radius of 64 meters. If the riders go through the loop at a speed of 48 meters per second, what's the centripetal acceleration? Okay, this is great. Centripetal acceleration is just velocity squared divided by the radius. So we're going to take 48 meters per second, square it, and divide it by 64. That makes the centripetal acceleration 36 meters per second squared. So I've got a rider with a mass of 80 kilograms, and I want to know the normal force acting on him while he's in the loop. So here's where we have to do net force stuff, because it's asking about forces. Net force is equal to mass times centripetal acceleration. Well, I have all that information. So from there, I can see the net force is 80 kilograms times 36 meters per second squared, 2,880 newtons. But I know the only force acting on this guy while he's in the loop is the normal force, so that 2,880 newtons is equal to the normal force. That's all we have to do. How far must the roller coaster go? How fast must it go for them to feel an acceleration of 50 meters per second squared? Centripetal acceleration is v squared over r, but here I want the acceleration to be 50, so that's going to equal the velocity squared divided by the same radius as 64 meters. So we're going to multiply both sides by 64. That goes away. When we do that, we get 3,200 newtons is equal to the velocity squared. So we're going to take that, square root both sides, and that velocity comes out to be 56.6 meters per second. That's how fast we have to go to get this bigger centripetal acceleration. All right, so for this luge run at the Olympics, we have a sled rounding a horizontal curve, radius 8 with a speed of 20. What's the centripetal acceleration of the sled? All right, well, to get centripetal acceleration, as always, we're going to say that it's the velocity squared divided by the radius. So the centripetal acceleration is 20 squared, our velocity, divided by the radius of 8 meters. You put that in, your centripetal acceleration comes out to be 50 meters per second squared. What's the normal force exerted by the track on the sled? This is the force that's making us go around the circle. It's the only force acting. So we know that the net force is equal to the normal force. Again, normal force is the only force that is in the direction of the circle. We also know that net force is equal to mass times acceleration. So it's 120 kilograms times an acceleration of 50 meters per second squared. So what I see here is that the net force is 6,000 newtons. That's the same thing as the normal force. So my normal force is 6,000 newtons. All right, for number 8, we have a new fighter jet. We're going to go in a horizontal loop with a speed of 340 meters per second, and I want to know the minimum radius it can fly so the acceleration doesn't exceed 50. So for this, we're talking about centripetal acceleration. I know that centripetal acceleration is v squared over r. I want that centripetal acceleration to be 50. I know my velocity is 340 meters per second squared. I'm trying to find the radius. So we're going to go ahead and square that out. 50 is equal to 115,600 divided by r. We're going to multiply both sides by r. It gets rid of the r. We want the r by itself now that it's on top. So we're going to divide by 50. So r is equal to 115,600 divided by 50, or 2,312 meters. At this radius, how long would it take the test pilot to complete one loop? Well, that question, how long will it take to complete one loop, is asking very specifically about the period of the plane. It's asking what is one period. What we're going to do is say, okay, my velocity is 2 pi r over the period. So my velocity, 340 meters per second, is equal to 2 times 3.14 times the radius of 2,312 meters divided by the period. We want to solve for the period. We're going to multiply both sides by the period, divide both sides by 340. Period goes away, the 340 stays. And so when we calculate it out, the period is equal to 42.7 seconds. That's how we would find the period.